Welcome to Orbit Observer. Settle in. Let the lights go low, let your shoulders drop away from your ears, and let whatever you are carrying today go quiet for a while. You don't have to do anything now. You don't have to solve it. You can just lie here in the dark and let me tell you about something far away. Something that has been happening slowly, without any hurry at all, for longer than you can imagine. I want to start with a small, strange thing. A salt. A very particular kind of salt that, by every rule we understand, should not still be there. It's a salt that, once it reaches the cold, airless surface of a distant little world, begins to fall apart almost immediately. Not over millions of years. Not over thousands. Within about 100 years, maybe less, it dries out and crumbles into something else, undone by the vacuum and the dryness of that surface. A human century. And it's gone. That is a blink. That is nothing in the long, slow arithmetic of space. And yet, when a small spacecraft leaned in close and looked, there it was, glowing, sitting on the surface, fresh, in a bright pale patch inside a crater named for the goddess of grain. This salt that should have vanished within a lifetime or two was simply there, present, undecayed, catching the faint far sunlight in the middle of a place called Cerealia Facula, on a world called Ceres. And there is only one gentle explanation for a salt that keeps disappearing but never quite goes away. Something must keep bringing it back. Something must be pushing more of it up, quietly, continually, from somewhere deep below. Which means that little world is not a finished thing. It is not a frozen relic, a cold stone left over from the beginning and stopped forever. It is still moving. Somewhere far beneath its icy skin, salty water is still rising, still seeping up through cracks in the crust, still reaching the surface and drying into white salt in the dark. Slowly, patiently, right now, more or less, as you lie here, as you breathe. That is what I want to tell you about tonight. A dwarf planet, out between Mars and Jupiter, that is quietly bleeding brine to its surface. A world that never fully went still. A slow, deep, hidden calm rising up through the cracks. And I think, if your mind is the kind that won't stop churning at night, if you know that feeling of lying in the dark, with everything turning over and over beneath the surface, refusing to settle, then maybe there's something soothing in this. Because here is a whole world doing exactly that, churning slowly below its own surface, and it doesn't need to be watched. It doesn't need you to fix it or finish it. It just keeps moving, gently, on its own, in the cold and the quiet, whether anyone is looking or not. You can let it. You can let the deep thing move without you tonight. So let it. Let it rise. Before we go down into it, I'd love to know where you're drifting off from. Tell me, somewhere in the comments, where in the world you are listening from tonight. What city, what country, what quiet room, what hour it is where you are. I read them. I genuinely like knowing that all of us, scattered across so many places, are lying in the dark, listening to the same slow story about the same faraway world. And if you're new here and you find that this kind of slow, unhurried journey helps you let go of the day, you can subscribe, and there will be more of these waiting for you whenever you need them. No rush. Whenever you like. Now, let's go to Ceres. To find it, you have to leave the Earth behind and go outward, past the orbit of Mars, into the wide, dim region we call the asteroid belt. That's the loose ring of rocky bodies that circles the Sun between Mars and Jupiter, Not a crowded field of tumbling stones like you might picture, but a vast, mostly empty space with scattered fragments drifting far apart in the cold. And in all of that, spread across all that emptiness, one object stands out, one body is the largest of them all. And that is Ceres. Ceres is about 940 kilometers across. That's roughly 585 miles side to side, which, on the scale of planets, is small. You could lay Ceres down across a good stretch of a continent. It's about the width of some countries. It is not a giant. And yet, in that whole belt of rubble and rock and drifting debris, Ceres is so much bigger than everything else that it holds, all by itself, something like a quarter to a third of the entire mass of the asteroid belt. Think about that for a moment, all those countless bodies, all those millions of scattered rocks strung out around the sun, and one single round world carries roughly a third of all of it. A hidden heavyweight. The quiet giant of a quiet place. It's large enough, in fact, and round enough, and settled enough under its own gravity that we don't just call it an asteroid anymore. Ceres is a dwarf planet. It is the only dwarf planet in the inner solar system, the only one this close to us, this side of the cold outer dark, where Pluto and the others drift. So it sits in a strange and lonely category, all its own. Too big to be just another rock in the belt, too small and too far to be a proper planet. A little round world, in between, largely overlooked, carrying more than its share of the neighbourhood on its back. It circles the sun at about 2.77 astronomical units. And that phrase, astronomical units, just means we're measuring in Earth distances. 1 astronomical unit is the distance from the Earth to the Sun. So Ceres is nearly 3 times farther from the Sun than we are. Almost 3 times the length of that lifeline of light and warmth that keeps our own world alive. Out there, the Sun is smaller in the sky. Dimmer, it gives less. And Ceres, moving slowly along its wide track, takes about 4.5 Earth years to make one full loop around it. 4.5 of our years for a single one of its own. While you live and change and grow older down here, out there it is still finishing the same patient circle it was on when you started listening. And it is cold. Deeply, thoroughly cold. The surface temperature on Ceres hovers around -100 degrees Celsius, and colder still at the poles, colder in the shadows. That is a cold with no real comparison in ordinary life. It is the kind of cold where water doesn't flow and doesn't drip and doesn't pool. It's the kind of cold where any water simply becomes ice, hard as rock, and stays that way, locked, still, frozen into the ground. In the deepest, permanently shadowed craters, where sunlight has never once reached in all the ages of the solar system, ice can sit stable and untouched, indefinitely, in the dark. A world where cold is not weather. Cold is the permanent condition of everything. And hold that thought, hold that image of a small, frozen, -100-degree world, because it makes what's happening beneath the surface all the stranger and all the gentler. On the outside, everything about Ceres says finished, frozen, stopped, and yet. We have known about Ceres for a long time, by the way, much longer than we've known most of the small bodies out there. It was discovered on the very first day of the 19th century, the 1st of January, 1801, New Year's Day. A Sicilian astronomer named Giuseppe Piazzi, working from an observatory on the island of Sicily, was carefully mapping stars when he noticed one faint point of light that didn't quite belong. Night after night, it moved. Just slightly. Just enough. Stars don't do that. Only something closer, something orbiting our own sun, drifts against the fixed background that way. And so, on the first night of a new century, a patient man watching the sky picked out one small wanderer that no one had ever seen before. For a while, people thought he'd found the missing planet. There was a long-standing suspicion back then that there ought to be a planet in the gap between Mars and Jupiter, a hole in the tidy spacing of the solar system that seemed to be waiting to be filled. And when Ceres turned up right in that gap, it seemed, for a moment, that the puzzle was solved. The missing planet, found at last. But then more small bodies were discovered nearby, and then more, and it became clear that Ceres wasn't a lone planet in an empty gap. It was the biggest member of a whole crowded belt. So it was reclassified, first as an asteroid, just one among many, and then, much later, in 2006, elevated again to dwarf planet. It has spent its whole known history being renamed and reconsidered, moved from category to category by people trying to decide what it is. And through all of that human argument, it just kept circling, unbothered, exactly as it always had. Piazzi gave it a name, and the name matters because it threads all the way through this story. He named it Ceres, after the Roman goddess of agriculture, the goddess of grain, of the harvest, of things that grow up out of the ground. It's the same root that gives us the word cereal. The breakfast in your cupboard carries the name of this little frozen world, or rather they both carry the name of the same old goddess of the fields. There's even a chemical element, cerium, named in Ceres's honour, discovered not long after the world itself. And here's a thing I find quietly lovely, a small poetry that the scientists who mapped it seem to have felt too. When they named the features on Ceres, the craters, the bright spots, the peaks, they kept to the theme. They named things for growth, for harvest, for agriculture. The great crater we're going to spend our night inside is called Occator, after the Roman god of harrowing, the god of breaking up and preparing the soil. The bright dome at its heart is called Cerealia Facula, after Cerealia, the Roman festival of grain. The scattered bright patches nearby are the Vinalia Faculae, after Vinalia, the Roman festival of wine. So this whole cold, distant, frozen place is named, top to bottom, for growing things, for fields and harvests and the slow work of the soil, a world named for growth and fertility and things rising up out of the ground. And it turns out that name is more fitting than the people who chose it could have known. Because Ceres, this world named for the goddess of the harvest, this world named for things that rise up through the earth, is quietly producing something. Not grain. Salt. It is pushing pale white salt up through the cracks of its crust, slowly from something wet and moving far below. A world named for growth, still growing something in the dark. Occator, the god of the tilled and broken soil, holds a crater whose floor has been broken and cracked, and up through those cracks the water rises. The names fit almost too well, almost like the world was waiting all along to live up to them. Now, I said water. And on a world where the surface sits at -100 degrees, where any water you could find is frozen hard as stone, that might sound strange. But this is one of the most surprising and gentle facts about Ceres, and it's the fact that everything else tonight grows out of. Ceres is not a dry rock. Ceres is a water world. Not water like our oceans, blue and open under an open sky, but water, real water, in enormous quantity, is one of the main things Ceres is made of. When scientists study its density, essentially how much it weighs for its size, and when they look at the way it holds its shape, The answer that comes back is that a very large fraction of this little world is water. Much of it locked away as ice, forming a thick outer shell, an icy crust, wrapped around a rocky, muddy interior below. Ice on the outside, rock and mud within, and, as we'll come to, something wet and briny in between. That puts Ceres into a small and remarkable club. There's a category of worlds that planetary scientists have grown very excited about over the last few decades, the ocean worlds. Worlds that, despite being far from the sun and frozen on the outside, are thought to hold liquid water somewhere beneath their icy shells. The two most famous are moons of the giant planets. There's Europa, a moon of Jupiter, wrapped in cracked ice, believed to hide a deep global ocean of liquid water underneath. And there's Enceladus, a small bright moon of Saturn, which we've actually watched jetting water out into space through cracks near its south pole. These are the celebrated ones, the poster children for the idea that liquid water and maybe, just maybe, the conditions for life might exist in hidden pockets all across the cold outer solar system. And Ceres, quietly, belongs in that conversation. Ceres is considered a candidate ocean world too. Not out in the far reaches, orbiting a giant planet, but much closer to us, right there in the asteroid belt, the nearest belt of debris. The region we've been sending spacecraft through for decades on their way to somewhere else. An ocean world, or something like one, hiding in plain sight, in a place we thought we understood. Not a clean open ocean, we'll be careful to say. The truth is subtler and stranger than that, and we'll get to exactly what's down there. But water, liquid water, salty and deep and slow, tucked beneath the ice of a world named for the harvest, close enough that a patient little spacecraft could go and see. And that is what makes this so quietly astonishing. We tend to imagine that the interesting, living, moving worlds, the ones with water still shifting inside them, with activity, with something ongoing, must be far away, exotic, hard to reach, wrapped around distant giant planets in the outer dark. But one of them was sitting right here the whole time, the largest body in the asteroid belt. The little dwarf planet Piazzi, found on a New Year's morning 2 centuries ago. All that time it was carrying an ocean's worth of water inside it, and, in at least one place, still moving it, still lifting it, still leaving its salt on the surface like a slow signature written again and again in the dark. I want you to hold the whole picture of it for a moment, before we go closer. Because the scale of it and the silence of it is part of the calm. Picture a small round world, 940 kilometers across, no bigger than a modest country laid flat. Picture it far out from the sun, nearly 3 times our own distance, so that the sun in its black sky is a smaller, weaker thing than the one you know, giving a thinner light and almost no warmth. Picture it moving slowly along a wide, patient orbit, taking 4.5 of our years to complete a single loop, drifting through the scattered emptiness of the asteroid belt with the nearest neighbours so far off they're just points of light. Picture its surface, grey and cratered and cold, frozen to -100 degrees, older than anything you have ever touched. Marked by impacts from ages so deep they have no human names. A quiet, still, frozen face, turned out to the dark. And then picture, beneath that still face, something moving. Water, briny, salty, cold but liquid, held in the deep, slowly shifting, slowly rising, finding its way up through fractures in the ice, seeping toward the surface with the patience of something that has all the time in the world and no reason to hurry. a slow current in the dark of a frozen world, a deep, hidden motion that never fully stopped. There is something in that image that I find settles the mind. Not because it's dramatic. It isn't. There are no explosions here, no roaring geysers, no catastrophe. Just slow, quiet, continuous motion, far below a still surface, going on and on, whether anyone watches or not. The kind of motion that doesn't need you. The kind of motion you can simply trust to keep happening while you rest. If your own mind tonight feels like a surface with too much moving underneath it, then maybe it helps to think of a whole world that lives exactly that way, and lives it peacefully. The churning below the surface isn't a problem to be fixed on Ceres. It's just what the world is doing. It's just the deep thing, moving, as it always has. So that is where we're going tonight. Down through the ice of a small frozen world named for the goddess of grain, to a crater named for the god of the broken soil, where a bright dome of salt sits glowing in the faint far light, salt that should have vanished long ago, salt that keeps coming back, salt left behind by water that is still slowly rising through the cracks. But before we go all the way down, I want to tell you about the traveller that carried us there. Because we didn't see any of this from Earth. From here, across all that distance, Ceres is only a faint point of light, the same wandering speck Piazzi noticed on that New Year's morning. Everything we now know about the water inside it, about the salt on its surface, about the slow motion in its depths, all of it came from a single, small spacecraft that made an extraordinarily patient journey across the solar system to go and look. A machine built by people, launched from our world, that spent years quietly crossing the dark to reach this quiet place. And it did something no spacecraft had ever done before. Its name was Dawn. And Dawn is, in its own way, the perfect companion for a story like this, a story about slowness and patience and continuous gentle motion. Because of all the ways we've built to travel through space, Dawn used one of the slowest and most patient there is. Most spacecraft you've heard of are thrown out into space by chemical rockets, great violent bursts of burning fuel, enormous thrust for a few minutes, and then the long silent coast afterward with the engines cold and dark, fast, loud, and brief. But Dawn didn't work that way. Dawn travelled on ion propulsion. Let me tell you what that means, gently, because it's a lovely thing. Instead of burning fuel in a great roar, an ion engine takes a gas, in Dawn's case, xenon, and it gives its particles a tiny electric push, throwing them out the back of the spacecraft very, very gently, but continuously. The thrust at any single moment is almost nothing. People describe it as about the force of a sheet of paper resting on your hand. That's all. You would barely feel it. It could not lift a feather here on Earth. But it never stops. Day after day, month after month, year after year, that whisper-soft push keeps going and going and going. And because it never stops, it slowly adds up. A tiny push, given patiently for long enough, builds and builds until the spacecraft is moving at tremendous speed, faster than any sudden burst could easily manage. Not through force, through patience. Through a gentle push that simply refuses to quit. I don't think I need to point out how well that fits the rest of tonight's story. A tiny, continuous, patient force, so soft you'd hardly notice it, that accomplishes something enormous simply by never stopping. That's the ion engine that carried Dawn, and it's also, more or less, the brine rising through the cracks of Occator, and it's also, if you like, the way sleep itself comes, not in one great effort, but in a slow, soft, continuous letting go that adds up, quietly until you're all the way under. Nothing forced, just a gentle push that doesn't stop. Dawn rode that patient push to do something no machine had done before it. It became the first spacecraft ever to orbit a dwarf planet. The first to go all the way out and settle into a steady circle around one of these small in-between worlds, rather than just flying past and glancing back. And it did something even rarer than that. Dawn became the first spacecraft in all of history to orbit two separate worlds beyond the Earth on a single mission. Because before it ever reached Ceres, it stopped somewhere else along the way. Its first destination was Vesta, the giant asteroid, the second largest body in the belt after Ceres itself, a battered, rocky world of its own. Dawn arrived at Vesta and slipped into orbit around it, and it stayed there, circling, studying, mapping that ancient surface through 2011 and into 2012. And then it did the thing that ion propulsion makes possible and chemical rockets almost never could. It gently lifted itself back out of Vesta's gravity, out of orbit around one world entirely, and set off again. That soft, continuous push once more across the belt toward the larger prize. Toward Ceres. To leave one world's orbit and go and enter another's is a thing that had simply never been done. Dawn did it on a whisper of xenon and years of patience. And it arrived at Ceres on the 6th of March, 2015. After the long crossing, after Vesta, after all those years of that soft, unrelenting push, the little spacecraft finally slid into orbit around the largest body in the asteroid belt, the frozen dwarf planet named for the goddess of grain. And it began, slowly, to look. We'll go with it, in a little while, down toward the surface, down toward the crater and the bright dome and the strange fresh salt that shouldn't be there. We'll see what Dawn saw as it came in close, two impossibly bright points of light burning in the grey, so bright and so strange that for a while, back on Earth, people didn't know what to make of them at all. Some of them, half joking and half wondering, whispered about lights, about something artificial, about who knows what shining up from a world no one had ever seen up close. The truth would turn out to be quieter than that, and, I think, far more beautiful. But that comes soon. For now, just hold the picture and let it be enough. A small frozen world out past Mars, named for the harvest. An ocean's worth of water sleeping inside it, and in one deep place, still slowly moving. A crater named for the broken soil, with a bright patch of salt at its heart that keeps appearing and should keep vanishing, but never quite does. And a patient little spacecraft, riding the softest push we know how to build, crossing years of empty dark to go and see. And settling at last into a slow, steady circle around it all, watching, the way I'll keep watch tonight while you drift. There is nothing here for you to do, nothing to solve. The deep thing is moving on its own, the way it always has, the way it will keep doing whether you're awake to know it or not. You can let your thoughts settle now, the way salt settles, slowly out of still water. You can let the surface of your mind go quiet and trust that whatever is moving underneath it will keep its own slow, patient rhythm without you needing to watch. Let's go a little closer now, down toward the grey cratered face of Ceres, down toward that one bright, glowing patch in the dark. Let me show you what Dawn found there, and why a salt that should have crumbled to nothing within 100 years was still sitting on the surface, still catching the thin far light, still being lifted grain by grain out of the deep and slow water below. Stay with me. We're only just beginning to descend. The spacecraft that made the journey did not rush. That is perhaps the most important thing to understand about Dawn. Before we follow it all the way to Occator's rim, it did not rush, it could not rush, and in some quiet way I think that unhurriedness is part of what makes it the right instrument for a story like this one. A story about patience, about slow and hidden movement, about something that has been pressing upward through cold rock for millions of years without any particular sense of urgency, without any interest in being seen. Dawn was not a fast spacecraft. It did not fire a great chemical engine and leap out across the solar system on a single bold arc the way a cannonball leaves a barrel. It moved the way a thought sometimes moves through the mind in those last moments before sleep, gathering, accumulating, almost imperceptible in any single instant, but building over time into something that crosses the whole dark expanse between here and there. The engine Dawn carried was an ion drive, a technology that sounds almost too gentle for the word propulsion. It worked by taking a noble gas, xenon, and stripping electrons from its atoms to turn them into ions, charged particles, and then accelerating those particles with electric fields until they streamed out of the back of the spacecraft at extraordinary speed. The thrust produced was tiny. At any given moment, the force Dawn's ion engines exerted on the spacecraft was roughly comparable to the weight of a single sheet of paper resting on your open palm. You would not feel it. You would not notice it at all. And yet, because that whisper of a push never stopped, because it ran for years and years patiently, the way brine presses against a crack in rock, the accumulated velocity change was enormous. Dawn was in the end one of the most maneuverable deep space probes ever built, not because it was powerful, but because it was relentless. Soft and relentless. The way water is. It launched in September of 2007 and spent the better part of 4 years crossing the asteroid belt before it eased itself, with quiet precision, into orbit around Vesta, the second largest body in the belt, a battered, pockmarked world of rock, scarred and ancient. Dawn stayed at Vesta for over a year, from July 2011 through September 2012, mapping its surface, measuring its gravity, reading the story written in its craters. And then it did something no spacecraft had ever done before. It fired its ion engine again, pulled free of Vesta's gravity, and headed deeper into the belt, toward the larger world waiting further out. No spacecraft before Dawn had ever orbited 2 separate extraterrestrial bodies. Getting into orbit is expensive in terms of fuel, in terms of the velocity changes required, and once you have spent that fuel arriving somewhere, there is usually nothing left to leave again and go somewhere else. But the ion drive changed that equation. Because the thrust was so low and so continuous, because it built momentum the way water builds pressure behind a dam, Dawn had enough flexibility in its trajectory to do the unprecedented thing, arrive at Vesta, stay, study, leave, and then arrive at Ceres. First mission to orbit a dwarf planet. First mission to orbit 2 separate extraterrestrial bodies. Both firsts belonging to the same small patient craft, running on the softest push we know how to build. It arrived at Ceres on March 6, 2015, and it had been seeing the lights for weeks before that. As dawn approached and Ceres grew slowly from a smudge in the dark to something that had surface features, something that had texture and shadow and varying brightness, the camera began to resolve the crater. Occator, and inside Occator. 2 points of light so intensely bright against the grey cratered surface that they didn't look quite like anything the mission scientists had expected. They were not just reflective patches, they were startlingly, almost defiantly, luminous, brighter by a large margin than anything else on the surface of Ceres. Brighter, in fact, than they had any obvious geological right to be. The early images that circulated, still blurry, taken from a distance, the crater still just a rough bowl, and the bright patches two smears of overexposed white, prompted the kind of speculation that tends to happen when a genuinely strange thing resolves slowly out of the dark. People wondered aloud, half joking, whether they might be lights, whether they might be evidence of something constructed, something deliberate. The phrase alien lights appeared in headlines. It was not serious science, and the scientists themselves were careful and measured, but the images were real, and the brightness was real, and before the full picture arrived there was a moment, brief but genuine, when the human mind stood at the edge of the unknown and felt the old familiar vertigo. The truth was quieter than that, and stranger, in its way, than the speculation. What Dawn's cameras eventually resolved, as the spacecraft settled into orbit and the images sharpened, was not light sources in any active or constructed sense. They were reflections. Intensely, almost impossibly bright reflections of the thin sunlight that reaches that far out. At 2.77 astronomical units from the Sun, Ceres receives only about 1/13 of the sunlight that falls on Earth. But what reaches it is real, and the bright patches at the center of Occator were bouncing it back with a reflectivity, an albedo, in the language of planetary science, far exceeding the dull grey rock around them. Something at the center of that crater was not rock. And it was not ice, at least not plain water ice, which would eventually sublimate away in the partial vacuum at Ceres's surface. It was something that could persist, something that could accumulate, something that left a residue. But before we follow that residue to its source, it is worth sitting for a moment with the crater itself, because Occator is not incidental to this story. It is the story. Or at least it is the vessel that holds the story, the bowl that caught what came up from below, and its own history matters. Occator Crater is roughly 92 kilometers wide. To put that in terms that might mean something as you lie in the dark, 92 kilometers is about the distance from one edge of a large city to the far suburbs on the other side if you drove in a straight line. It is not the largest crater on Ceres, but it is among the more geologically complex, and its complexity is what made it, in the end, the most interesting place on that world. It formed approximately 4 million years ago, when something, an asteroid, a chunk of rock somewhere between a few hundred meters and perhaps a kilometer or two across, struck the surface of Ceres with enough energy to excavate a bowl nearly 100 kilometers wide and several kilometers deep, fracturing the crust below it, releasing enormous heat and sending a shockwave through the ice and rock shell of the planet like a bell being struck. The crater that remained is what we see now, a roughly circular basin with a raised rim, a flat floor, and at its center a smaller depression, a central pit, the kind that forms in craters on icy worlds when the material at the center rebounds and then subsides after the initial impact. It is inside that central pit, at the heart of the crater, that Cerealia Facula sits. The name comes from the Roman festival of Cerealia, the spring celebration held in honor of the goddess Ceres herself, the days of games and prayers for the grain harvest, when Romans dressed in white and lit torches and ran through the night. The name was given by the International Astronomical Union, which has themed all of Ceres's named features around agriculture and harvest. Occator himself was the Roman deity of harrowing, of breaking the soil before planting, The Cerealia Faculae, the second cluster of bright patches to the east, take their name from the Roman wine festival. Ceres herself, the world, carries the name of the goddess, from whose name we also get the word cereal. And the element cerium, isolated in 1803, just 2 years after Ceres was discovered, was named after that same first sighting. There is something quietly pleasing about the naming, a world made of water and salt, and the cold machinery of geology, dressed in the language of growth and harvest, of the earth opened and planted and tended and fed. Cerealia Facula, the central bright dome, is roughly 9 to 10 kilometers across. It sits in the central pit of Occator, like something placed there deliberately, a white mark in a grey bowl in a grey world. Around it, extending outward from the central pit across the crater floor to the east, the Cerealia Faculae scatter in a looser, more diffuse pattern, bright patches, but less concentrated, less intensely white, more like spilled powder than a single dense deposit. The two regions are related, but not identical, and as the science developed, they turned out to have somewhat different stories to tell about their origin and their age. Cerealia Facula, the central one, is the older of the two in one sense, and also, in another and more important sense, the one with the most recent additions. Dawn's framing cameras mapped the surface of Ceres across multiple orbits and multiple observing geometries, building up a picture of the terrain with enough resolution to see individual boulders and small secondary craters. But the discovery of what the bright material actually was, the identification of the chemistry, the reading of the composition came from a different instrument altogether. Dawn carried a visible and infrared mapping spectrometer, referred to by the mission team as the VIR. A spectrometer, in the simplest possible terms, is an instrument that reads color with extraordinary precision, not just the colors the eye can see, but the infrared colors that lie beyond the red end of the visible spectrum, invisible to us but rich with chemical information. Different minerals and compounds absorb and reflect light at different specific wavelengths, like fingerprints, and a spectrometer that measures those wavelengths carefully enough can identify what something is made of from a distance, from orbit, without ever having to touch it or collect a sample. It reads the light that comes back from the surface and finds in it the chemical signatures of whatever is sitting there, baking, or more precisely, freezing in the thin sunlight. The VIR pointed at Cerealia Facula and the Cerealia Faculae, and it read the light, and it found salt. Primarily sodium carbonate. That is the main constituent of the bright material at Cerealia Facula, a salt you might know, in a slightly different context, as soda ash or as natron, the mineral the ancient Egyptians used for mummification and ritual purification. It is a sodium salt of carbonic acid, white and fine, and in the right conditions it forms as a crust, as an evaporite. The residue left behind when water that has sodium carbonate dissolved in it evaporates or sublimes away, abandoning its dissolved cargo as a dry deposit on whatever surface it was resting on. Like the white lines left at the edges of a tide pool when the water pulls back. Like the ring left inside a glass. Like the thin crust of salt that appears at the margins of a desert lake as the water retreats in summer. The sodium carbonate at Cerealia Facula was, the VIR was saying, the mark left by water that had been there and then left. Not the water itself, the memory of the water, the record, written in white, of where it had been. Along with the sodium carbonate, the spectrometer found ammonium chloride, another salt, one that forms when ammonium-bearing compounds react with chloride-bearing ones, again in the presence of water. And there were other salts in the mix, a chemistry that looked to the scientists analyzing the data like the signature of a specific kind of water. Brine. Not clean water, not ice melt from the crater surface, but deeply saline, mineral-laden water of the sort that comes from deep underground, from places where water has been sitting in contact with rock and mineral for a long time, absorbing what the rock has to offer, growing heavy with dissolved salts, growing denser and harder to freeze, carrying in its chemistry the record of its long underground history. This identification was published in 2016 by Maria Cristina de Sanctis and her collaborators in the journal Nature, and it was a genuinely significant result. The bright spots were salt, not alien lights, not a geological anomaly without precedent, not an artifact of illumination or camera calibration. Salt, the residue of brine, the tide mark of water that had risen and then evaporated or sublimated in the airless cold of Ceres's surface, leaving its chemistry behind as a white deposit that caught the light. It was a satisfying answer, and it raised almost immediately a deeper and more interesting set of questions. Because the crater, as we have established, formed roughly 34 million years ago, and the sodium carbonate salt deposits at Cerealia Facula are not 34 million years old. They are not even a fraction of 34 million years old. The salt at the center of the central bright spot, the Cerealia Facula deposits, has been dated to approximately 2 million years of age. In some areas, the material appears even younger than that. The crater itself is ancient. By human reckoning, 34 million years is a time before our genus existed, before most of the mammal families we recognize today had settled into their modern forms, a time when the world was different in nearly every particular. And yet the salt sitting inside it is geologically fresh. 2 million years on a world that has been geologically active for billions is essentially yesterday. It is the last page of a very long book. The crater did not make that salt when it formed. The impact happened 34 million years ago, and the salt appeared most recently, about 2 million years ago, and has been appearing since. Something else made that salt, something that came later, and came from deeper, and has been coming perhaps ever since. Dawn's cameras and spectrometer gave us the what. They told us the bright spots were salt, told us the chemistry, told us the age. But the deeper mystery, the mechanism, the plumbing, the source of the water that left this residue 2 million years after the impact that opened the crater. That required more than surface observation. It required reading the gravity. It required getting closer. And it required, ultimately, the final, lowest chapter of Dawn's long life above Ceres. The spacecraft had been orbiting since 2015. It had descended through a series of progressively lower orbits, mapping the surface with increasing resolution, reading the chemistry from shorter and shorter distances. The VIR data that identified the sodium carbonate in 2016 came from one of the intermediate orbits. But in the final phase of the mission, in the months before the propellant ran out and the spacecraft fell silent, Dawn was brought as low as approximately 35 kilometers above the surface. 35 kilometers. To imagine what that means in practical terms, if you were standing on the surface of Ceres and you could look straight up, Dawn at its lowest point would have been closer to you than many people's daily commute to work. A spacecraft that had crossed the asteroid belt twice, that had orbited 2 worlds, that had spent years in the dark between planets, sitting at the end, barely above the horizon, gathering the most detailed observations of its entire mission from that intimate altitude. It was at this altitude that the gravity measurements became precise enough to detect what was hiding beneath the crater. And it was at this altitude that the spectrometer, working in those final months, gathered the data that would lead to the most important single discovery the mission had to offer. The discovery published not in 2016 but in 2020 in a suite of papers appearing in the journals Nature Astronomy, Nature Geoscience, and Nature Communications, produced by the Dawn Science team under the leadership of Carol Raymond and including the work of De Sanctis, Jennifer Scully, Andreas Nathius, and their collaborators. What the gravity measurements showed, and gravity is a patient, honest detective because it responds only to mass, and mass cannot lie, was an anomaly beneath Occator Crater, a region of higher than expected density below the crater floor, something denser than the surrounding rock and ice. Something that, given what the surface chemistry was already saying about brine, was consistent with liquid or near-liquid material, a reservoir of something heavier than ice, something with more mass per unit volume. Sitting down there in the dark, roughly 40 kilometers beneath the surface. 40 kilometers is deep. To put it in the context of something familiar, the deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, is about 11 kilometers below sea level. The deepest borehole ever drilled on Earth, the Kola Superdeep borehole in Russia, an extraordinary feat of engineering that took decades, reached just over 12 kilometers before the rock became too hot and plastic to drill further. 40 kilometers is more than 3 times deeper than we have ever managed to reach into our own planet. It is deep in the sense that it is, for practical purposes, unreachable, a place we know about only because of what it sends up, the way you might know about the bottom of a river only by what the current carries to the surface. The reservoir beneath Occator is not accessible, but its contents, it appears, are rising anyway. Not because anyone reached down for them, but because physics is patient and cracks, once opened, tend to let things through. The reservoir, according to the data and the modelling published in 2020, is not a small thing. It extends hundreds of kilometres in width, far beyond the boundaries of Occator Crater itself, deep below the surface of Ceres. It is not, to be precise about it, a pool of open liquid water sitting in a cavern the way water might sit in an underground lake. The more accurate picture is of a muddy, briny slush, a mixture of water heavily laden with dissolved salts and with rock particles and clays sitting under pressure in the pore spaces and fractures of the material at depth, not exactly flowing freely, but not exactly solid either. Something between a sponge soaked in brine and a very wet, very cold mud. Imprecision is easy here, and it is worth resisting. This is not an ocean, not in the sense that Europa's deep ocean beneath its ice shell is an ocean, not a globe-girdling body of liquid water kilometers deep. It is a regional feature, a brine-saturated layer at depth, extensive but not necessarily uniform, not clean and not clear. But it is there. The gravity says it is there. The chemistry of the surface says water from somewhere has been arriving and leaving its salt. And the fractures in the crater floor, the channels opened by the impact 34 million years ago, kept active by the residual heat that took millions of years to fully dissipate, are the conduits through which material from that deep, wet, briny layer has been making its way upward, slowly, patiently, over millions of years, and apparently still today. The impact itself did 2 things at once, and it is worth holding both of them in mind as you lie here in the dark. First, it fractured the crust, opened pathways, created channels, turned a solid shell into something cracked and permeable in ways it had not been before. Like a pane of glass that has been struck hard enough to web with cracks without shattering. Second, it released heat. An impact of that scale converts an enormous amount of kinetic energy into thermal energy at the moment of collision. The rock and ice, at the point of impact, heats suddenly and dramatically, melting, vaporizing, reshaping. And the heat then spreads outward and downward into the surrounding material, taking a very long time to dissipate. The crater floor and the material beneath it were warmer after the impact than they had been before, and they stayed warmer, slowly cooling, for millions of years. That residual heat, that long, slow, fading warmth in the rock, served as a kind of engine. Warm things rise when they are embedded in cooler surroundings, and the brine at depth, gently heated by proximity to the impact zone, would have had additional motivation to follow the fractures upward. Not in a rush, not in the dramatic fashion of a geyser or a volcanic eruption, but in the slow, patient fashion of groundwater finding its level, of brine working its way through permeable rock, the way sap moves through wood, molecule by molecule, pressure-driven, following the path of least resistance upward through the cracked and permeable crust, carrying its dissolved salts with it. And when it reached the surface, or came close enough to the surface that the vacuum above could pull it the rest of the way, the water did what water does in a vacuum. It evaporated. Or rather, it sublimated, transitioning directly from liquid to vapor without passing through the intermediate stage, the way dry ice disappears in air. The water left. The salts stayed. And over time, over 2 million years of time, or some substantial fraction of that, the salt accumulated where the brine had been reaching the surface most consistently, at the central pit of Occator Crater, building the deposit that Dawn's cameras eventually saw as the brightest spot on the entire surface of Ceres. That is the picture. Deep brine, pressed upward through cracked rock, losing its water to the vacuum, leaving its salt behind. A mechanism simple enough to describe in a sentence, and yet one that has been running apparently for millions of years and shows no clear sign of having stopped. Dawn's instruments, reading the surface from orbit, gave that picture its first clear outlines. The framing camera drew the topography, the shapes of the crater and its central pit, the dome of Cerealia Facula, and the scattered patches of the Venalia Faculae. The VIR read the chemistry: sodium carbonate, ammonium chloride, and then, in those final close approaches, something else. Something that the 2020 analysis would pull from the data and hold up as the single strongest piece of evidence that the briny plumbing beneath Occator is not a relic, not a memory, not a finished process that ran its course 2 million years ago and left a beautiful residue behind. But that comes in the next part of the descent. That is the piece of evidence that carries the most weight. The salt that should not still be there, and is. For now, let the picture settle. Dawn approaching across the dark, carrying its soft xenon push and its spectrometers and its framing cameras. The two bright points resolving out of the grey, not alien lights, but something rarer and more interesting, dried brine, old salt, the tide mark of water that rose. Occator's rim, 34 million years old, holding in its bowl a deposit 2 million years young. The instruments reading what the surface says, and the gravity reading what the deep says, and the two readings pointing, together, in the same direction, down and old and slow and still. You can let that settle the way salt settles. Dawn circling. the crater below. The brine, far below the brine, lower than anything we've drilled, deeper than the deepest reach of human technology applied to our own planet. Still there, still wet, still slowly following the cracks toward the surface the way it always has. You don't need to do anything with that information. You don't need to remember it, or hold it, or carry it anywhere. Let it simply sit in your mind the way a stone sits on the bottom of still water, while the water above it moves, while the surface reflects its small fraction of distant light, while everything settles and darkens and grows quiet. The spacecraft found the salt. The salt told the story. And the story, as it turned out, was not finished, not even close to finished, not even at 2 million years, not even now. But to understand why, we need to look more closely at one specific thing that Dawn found at Cerealia Facula in its final close passes. One specific salt. One that should not have survived the time it apparently survived. One that carries in its molecular structure a kind of clock, and what that clock says about when the water last arrived is the thing that gives this whole long, quiet story its most important word. That word is still. The salt came first, before the clock, before the reservoir, before the deeper mystery that made everything else make sense. The salt was what Dawn found in the first long, careful months of its Ceres orbit, when the instruments turned toward the brightness of Occator and the spectrometer began to read the chemistry of what lay there on the floor of a 34-million-year-old crater, glowing back at the spacecraft like something left out in the open. Like something that did not particularly mind being seen. And what it found was sodium carbonate. That name alone is worth sitting with for a moment. Sodium carbonate. Not ice, not silicate rock, not some exotic mineral compound unique to outer solar system worlds, but sodium carbonate, which is soda ash, which is natron, which is the same basic salt chemistry that the ancient Egyptians used in mummification, that bakers use in certain forms of pastry. That lakes in East Africa accumulate at their shores when the water evaporates away in the dry heat and leaves behind what dissolved in it. Sodium carbonate is a salt that forms from the interaction of sodium-rich water with carbon dioxide and its presence on the surface of a world in the asteroid belt tells you something specific, that water was here. That the water had dissolved things into itself along the way, and that when the water was gone, when it evaporated or sublimated off into the thin near vacuum of Ceres's barely there atmosphere, it left its dissolved cargo sitting on the surface like dried tide lines on the hull of a beached boat. You have seen this, maybe, on the rim of a teacup left on a windowsill. A little water, a little dissolved mineral, the water gone, and a faint white ring left behind where the surface tension held the last of the liquid before the drying finished. The white of Cerealia Facula is that ring, that residue, that mark left by water that was here and is no longer here in its liquid form, but left its chemistry behind so that something watching from orbit could look down and read it like a letter. The letter was signed by De Sanctis and her team, Maria Cristina De Sanctis, and her colleagues, who published the identification of Cerealia Facula's composition in Nature in 2016. In the early period of Dawn's science return, when the bright spots had just resolved from brilliant unidentified pixels into something the spectrometer could begin to characterize. Dawn's visible and infrared mapping spectrometer, the VIR, a compact instrument that reads the particular wavelengths of light reflected from a surface and matches them against the known signatures of different minerals and compounds, found the telltale absorption features of sodium carbonate. It found ammonium chloride alongside it. Together, these salts painted a coherent picture. Brine, liquid water laden with dissolved salts, had reached the surface, and the water had gone, and the salts had not. Ammonium chloride is worth a brief note of its own. It forms when ammonia-rich water meets certain acidic conditions, and its presence alongside sodium carbonate at Occator suggests that the water which rose through the crust carried a particular chemistry with it. A chemistry reflecting the deep interior of Ceres, a rocky, muddy, chemically complex interior where water had been in contact with rock for a very long time. Slowly dissolving things into itself the way slow-moving groundwater does, picking up whatever the rock it touches is willing to give. This is not pure water, pristine and simple. This is old water. Water that has been somewhere dark and pressured and intimate with rock for a long time. Water that has been changed by where it has been. And then, changed, it rose. That is what the spectrometer said in 2016. Salts, two kinds, consistent with brine that evaporated. The bright spots are not ice, they are not volcanic rock, they are not alien construction material, as some small, briefly entertained corner of the public imagination had hoped or feared or playfully suggested when the two dots first appeared on Dawn's approach images. They are salt, old dissolved minerals dried in place, the residue of water. And that would have been enough for most stories. That would have been, for most treatments of Ceres, the ending, mystery introduced, mystery solved, bright spots identified as salt from evaporated brine, everyone goes home satisfied. The chapter closes. The curiosity is quenched. You understand what you are looking at, and you can rest. Except the timeline did not cooperate. The timeline is where the story refused to end. Because Occator Crater is old. 34 million years old, formed when a large impactor struck Ceres's surface and blasted a hole 92 kilometers wide into the ice and rock and left behind a depression that has, since then, slowly slumped and settled and been partly modified by the slow, cold geological processes of a world in the deep cold of the asteroid belt. 34 million years. To put that in a register that has some human texture, 34 million years ago, on Earth, the Eocene epoch was drawing toward its close. Early forms of horses were beginning to look more like horses. The Antarctic ice sheet was beginning its long establishment, and the world that would eventually produce Giuseppe Piazzi and NASA and the Dawn spacecraft was still separated from those things by an almost incomprehensible length of time. 34 million years is not ancient by solar system standards. It is a relatively young crater, as large craters go. But it is a very long time in any scale of reference that a human mind can hold with some ease. The crater is 34 million years old. The bright deposits of Cerealia Facula are approximately 2 million years old. Those two numbers do not match, and the gap between them is the thing that changed everything. The thing that made the question not what are the bright spots, but why are they so new, when the bowl that holds them is so old? 2 million years. Again, that is not young by the standard of a human life, or a civilization, or the accumulated span of recorded history. But in planetary geology, in the context of a 4.5 billion-year-old solar system, 2 million years is a geological instant. The salt at Cerealia Facula was laid down long after the crater that contains it had already formed, long after the violent physics of the impact had finished their work, and the surface of Occator had begun its slow settling and equilibration. Something happened much later. Something that had nothing to do with the original impact event. Something that produced salt and left it in the central pit of the crater, young enough, fresh enough, that the dating methods available to the researchers could distinguish it clearly from the older, impact-related material elsewhere on the crater floor. The crater carved the bowl 34 million years ago. And then, 32 million years later, give or take, brine came up through the bottom of the bowl and dried there and left its residue behind. Those are two separate events, two separate processes, the impact, and then, much later, the upwelling. And that separation, that gap of 32 million years between the crater's formation and the deposit's youth, is the thing that demands an explanation the simple impact melted some ice and the melt evaporated story cannot provide. Because impact melt does not wait 32 million years to dry out. If the bright spots at Cerealia Facula were simply the dried residue of brine produced by the impact itself, the heat of the collision melting local ice, that meltwater mixing with rock, the resulting brine pooling in the crater basin and slowly evaporating over centuries, then the deposits should be roughly the same age as the crater. Old, ancient 34 million years, or close to it, with whatever uncertainty the dating methods carry. The salt should be as old as the bowl it sits in. It is not. It is 32 million years younger. And that difference is not a rounding error, not a margin of uncertainty, not a detail that might be explained away by the limits of the method. It is a real signal. Something was producing brine and delivering it to the surface of Occator long after the impact that made the crater had been, geologically speaking, over and done with and settling into cold stillness for many millions of years. Something beneath Occator has been slowly and persistently moving brine upward through the crust for a very long time, and the evidence suggests that something has not yet stopped. This is what the August 2020 papers set out to address. In August of 2020, a suite of studies appeared across 3 journals: Nature Astronomy, Nature Geoscience, Nature Communications, drawing on data that Dawn had gathered in its final, closest orbital pass. Descending to approximately 35 kilometers above the surface of Occator Crater, lower than it had flown at any earlier point in the mission, close enough that its instruments could read fine detail that had been impossible to resolve from higher altitudes. Carol Raymond and the Dawn science team, Maria Cristina de Sanctis, Jennifer Scully, Andrea Snathus. These were the names attached to the papers, the researchers who spent the months and years after Dawn's November 2018 silence working through the data the spacecraft had gathered in its last close approach, extracting from it an answer, or the closest thing to an answer the evidence would support, to the question the timeline had opened. Where was the brine coming from, and how long had it been coming? The answer, assembled from multiple independent lines of evidence and published across those 2020 papers in a way that allowed each line of evidence to speak without the others, was this: beneath Occator Crater, at a depth of approximately 40 kilometers, there is a reservoir of briny liquid, extensive, persistent, hundreds of kilometers wide, that formed long ago and has never fully frozen. 40 kilometers. That depth is worth pausing on. 40 kilometers is approximately 25 miles. It is deeper than any borehole human engineers have ever drilled into the Earth, and by a considerable margin, the deepest borehole ever completed on our own planet reached just over 12 kilometers before the rock became too hot and the project too technically overwhelming to continue. To reach 40 kilometers down into the Earth would require going more than 3 times deeper than that record. It is far below the deepest ocean trench. It is deep in the sense of being genuinely beyond human reach, even on the world we know best and have studied most thoroughly. And on Ceres, 40 kilometers down, there is water, salty, cold, under pressure, laden with the chemistry of the deep interior, but liquid, not frozen, not locked into crystal lattice, liquid, and therefore capable of moving, of responding to pressure gradients, of finding pathways through the rock and ice above it, the way that water always does. The way that water has always done everywhere that water has ever existed, in any form that allows for movement. Hundreds of kilometers wide. Not a pocket. Not a small isolated lens of liquid trapped by a local heat source. A reservoir. Extensive. Distributed beneath the region in a way that the word pocket fails to capture. The scale of it, a briny layer sitting deep beneath a surface area that could stretch from one side of a large state to the other, is part of what makes the Ceres story feel different from what most people assumed when they heard dwarf planet in the asteroid belt. The asteroid belt conjures images of dry, cold, inert rock floating in the dark. Fragments, rubble, the remnants of something that never quite coalesced into a planet. Not places where liquid water persists at depth, in vast cold reservoirs, quietly connected to the surface above through networks of fractures. And yet, the reservoir is briny because dissolved salts lower the freezing point of water. This is the same mechanism that makes ocean water freeze at a lower temperature than fresh water. The same mechanism that explains why we spread salt on icy roads in winter. Salt disrupts the formation of ice crystals, keeps water in its liquid phase at temperatures where pure water would have long since frozen solid. 40 kilometers down on Ceres, the temperature is cold, not the -100 degrees Celsius of the surface, but still very cold by any standard that would feel relevant to life as we know it. Pure water at that depth would almost certainly freeze. But brine, water with enough dissolved salt in it, can stay liquid at temperatures that would freeze its purer counterpart. And there is enough residual heat within Ceres, heat left over from the slow radioactive decay of elements in the rocky interior, heat that has been leaking outward through the insulating ice and rock shell for billions of years, very slowly, very patiently, to keep a briny layer liquid at depth, even at Ceres' distance from the sun, even in the cold quiet of the asteroid belt. The brine stays liquid because it is salty, and because it is deep, and because Ceres is not quite as cold inside as its surface suggests. These three things together produce a reservoir that has persisted, apparently, for an enormous span of time. And the impact that made Occator Crater 34 million years ago did something to that reservoir's relationship with the surface above it. The impact fractured the crust. This is the two-source plumbing that the 2020 papers described, and it is worth understanding with some care, because it is what explains both the old salt and the young salt, both the crater-related chemistry and the fresh Cerealia Facula deposits, both the shallow material and the deep material, all the different things that seem to require different explanations, held together in a single coherent system. When the impactor struck Ceres and blasted out a 92-kilometer basin in the surface, it did several things at once. It melted local material. It released heat, an enormous, violent, sudden pulse of heat from the kinetic energy of the collision, converting into thermal energy in the rock and ice. That heat melted some of the shallow ice in Ceres' outer shell and produced brine from the local material, brine that pooled and eventually evaporated, leaving behind the older, impact-related salt signatures elsewhere on the crater floor. This is the first source, the shallow source, the older chemistry consistent with the crater's age, the expected residue of a large impact on an ice-rich world. But the impact also fractured the crust. It cracked the ice and rock above the deep reservoir in ways that created pathways, conduits, fractures, channels through which fluid from far below could slowly travel upward. And the heat of the impact, though it dissipated over time, dissipated slowly enough in the insulating deep interior that it warmed the reservoir from above for a long time after the surface had cooled. The reservoir, already briny and already below its freezing point in terms of temperature balance, received an additional thermal pulse. The fractures above it opened. The brine, under pressure from the weight of the ice and rock above it, and now with a warm, cracked pathway available for the first time in that region, began to move. Not quickly. Nothing about this story is quick. The brine did not surge through the new fractures in a rush. It seeped. It crept. It moved the way water always moves through rock, finding the paths of least resistance, following the grain of the fractures, working its way upward over enormous spans of time because it had nowhere else to go, because the physics of pressure and the geometry of the fractures were pointing it, slowly, persistently, toward the surface. This ascent, the slow upwelling of brine from the deep reservoir through the impact-fractured crust above it, over millions of years, producing the young salt deposits at Cerealia Facula, is the second source, the deep source, the ongoing source, the one that explains the 2-million-year-old deposits in a 34-million-year-old crater. 2 stages, 2 chemistries, 2 timescales. The impact, and then, long after the impact had become ancient history, even by Ceres's geological calendar, the deep reservoir quietly finding its way up through the cracks the impact left behind, arriving at the surface, losing its water to the near vacuum above, and leaving its dissolved cargo behind as bright white salt on the floor of the central pit. This is the plumbing of Occator Crater, a system built by catastrophe and then operated quietly and without drama for tens of millions of years. The crater as the wound, and the wound as the channel, and the deep reservoir as the thing that has been slowly bleeding through the channel ever since. And there was one more piece of evidence, independent of the spectrometer, independent of the age dating, independent of the chemistry, a piece of evidence that came from gravity. Dawn carried a gravity science instrument, which is a somewhat abstract way of describing the precise measurement of how the spacecraft's orbit was being perturbed by variations in Ceres's gravitational field as the spacecraft passed over different regions of the surface. The gravity of a large body is not perfectly uniform. It varies from place to place depending on what is beneath the surface at each point. Dense rock pulls harder than porous ice, and a buried pocket of liquid brine, denser than the surrounding ice matrix, would exert a slightly stronger gravitational pull on a spacecraft passing overhead than the average of the surrounding terrain. Not a dramatic difference. Not something you would notice with any instrument less sensitive than the one Dawn carried, but measurable, given enough passes at close enough altitude, and given enough careful analysis of the tiny but real perturbations accumulating in the spacecraft's trajectory. Beneath Occator Crater, the gravity measurements revealed a density anomaly, a region of elevated density relative to the surrounding terrain, located beneath the crater in a position consistent with the inferred reservoir. Something denser than average was down there, something that pulled on Dawn, faintly, as the spacecraft curved through its orbits over the bright deposits, pulled on it in a way that rock alone would not explain. that ice alone would not explain, but that a volume of liquid brine, heavier, denser than the surrounding ice, would, the gravity data, weighed the reservoir from orbit. Think about that for a moment. In the quiet way this story invites. A spacecraft moving silently at 35 kilometers above the surface of a crater in the asteroid belt, its trajectory bent by fractions of a millimeter per second by the invisible tug of a liquid body 40 kilometers below, and instruments sensitive enough to read that bending, to turn the trajectory's tiny drift into a map of what is hiding deep inside the world below. The mass anomaly, as the researchers called it, the slight excess of gravitational pull beneath Occator, is one of the most remote and technical pieces of evidence in this whole story, and yet it is somehow the most concrete. There is something down there heavy enough to pull a spacecraft. You can weigh an underground reservoir of brine from an orbit above a crater on a dwarf planet in the asteroid belt, and Dawn did, and what it weighed was consistent with what the chemistry and the age dating and the fracture geology all independently pointed toward. A reservoir. Deep, wet, salty, still there. The three lines of evidence, the spectral chemistry of the deposits, the age mismatch between crater and salt, and the gravity anomaly beneath Occator, all arriving at the same conclusion from different directions, the way three separate expeditions setting out from different starting points and following different routes, all arriving at the same destination by morning. The destination is a deep reservoir of briny liquid beneath Occator Crater that formed long ago, that the impact cracked open access to, and that has been slowly, patiently delivering its contents upward through the fractured crust ever since. The 2-million-year age of the Cerealia Facula deposits means the process was still operating 2 million years ago, at the very least. But the 2020 papers, the science that Dawn gathered in those final close approaches before it fell silent, suggested something more unsettling and more quietly wonderful than that. The evidence suggested that the process is not 2 million years past. The evidence suggested that the process is not past at all. To understand why, you need to understand one more thing about the salt. Not the sodium carbonate, not the ammonium chloride. Those are the older chemistry, the established story from 2016, the foundation of the identification. You need to understand a different salt. A third compound found at Cerealia Facula in that final low-altitude data pass, a compound that the earlier, higher-altitude passes had not resolved clearly enough to identify with confidence, a compound that De Sanctis and her colleagues named in the 2020 Nature Astronomy paper, with a specificity that carried its own weight of implication. Hydrohalite, hydrated sodium chloride. NaCl 2HO. Table salt, ordinary sodium chloride, the kind you might shake onto food, the kind that dissolves instantly in water, but with two water molecules bonded into its crystal structure, locked into its lattice in the way that certain salts can incorporate water when they crystallize under cold, wet conditions. Hydrohalite is what sodium chloride becomes when it crystallizes from solution at low temperatures, the form it takes when cold brine is the medium and the conditions are right for the water molecules to be incorporated rather than expelled from the growing crystal. It is not an exotic compound. It is not something rare or bizarre in the catalogue of known minerals, but it had, before Dawn found it at Cerealia Facula, never been identified anywhere beyond the surface of the Earth. Not on the Moon. Not on Mars, not on any asteroid, any comet, any other body in the solar system where human instruments had looked. The first detection of hydrohalite off Earth was at Cerealia Facula, on the surface of Ceres, in Dawn's final close data pass, and it was published in August 2020, and it changed the significance of the bright spots in a way that the sodium carbonate identification, for all its importance, had not. Because hydrohalite is unstable. Not unstable in the sense of radioactive, not unstable in the sense of explosive or reactive. Unstable in the sense that it does not last. In the conditions at Ceres's surface, the near vacuum, the dryness, the exposure to space, hydrohalite dehydrates. The water molecules incorporated into its crystal structure are not tightly enough bound to remain in place indefinitely against the thermodynamic pressure of the surrounding environment, which is essentially zero humidity, essentially zero atmospheric pressure. Conditions that strongly favor the departure of any loosely held water from any surface it sits on. The hydrohalite loses its incorporated water molecules to the vacuum. It converts, over time, to anhydrous sodium chloride, ordinary table salt, the dry form, without the structural water. And this conversion does not take geological time. It takes approximately 100 years. Give or take, in the conditions at Cerealia Facula. Hydrohalite would dehydrate completely within something like a century. 100 years. 200 years at most, under generous assumptions about the local microenvironment. Against a backdrop of 2-million-year-old salt deposits and 34-million-year-old crater walls, a lifetime of 100 years is not even a rounding error. It is nothing. It is less than the blink of a geological eye. It is the kind of timescale that belongs not to planetary science, but to human history, the span of a few generations, the span of a brief dynasty, the span of whatever is currently sitting in your awareness as recent. Dawn found hydrohalite at Cerealia Facula, intact, present, still holding its incorporated water, not yet converted to the anhydrous form. Still in the hydrated state that requires, for its existence, that the conditions under which it formed have continued, that salty water has continued to reach the surface and crystallize there, continuously, within the span of what a human intuition might comfortably file under recently. A salt that should have vanished within a century, present and intact at the surface of a crater on a dwarf planet in the asteroid belt. There is only one explanation the chemistry permits. The brine has not stopped arriving. The reservoir below, 40 kilometers down, hundreds of kilometers wide, weighted from orbit by gravity, identified by its dried residue, confirmed by the impossible youth of its deposits, is still, slowly moving upward through the fractures, still reaching the cold surface of Occator, still evaporating and leaving its chemistry behind, still crystallizing hydrohalite in the central pit of Cerealia Facula in quantities sufficient to replenish what the vacuum destroys. Fast enough to keep the hydrated form present despite the constant slow loss to dehydration. Fast enough. Slow enough. Quietly, persistently, at whatever rate the physics of a deep reservoir and a fractured crust and a near-vacuum surface conspire to produce, a rate no human has measured directly, a rate no instrument has clocked with precision. At that rate, Ceres is still bleeding brine to its surface, and has been apparently within the span of time that hydrohalite can survive the conditions it finds itself in when it arrives. The salt is the clock. The clock is running, and the clock says, the water was here recently and is being resupplied now, and the process that brings it upward from 40 kilometers below has not yet stopped, may not yet be anywhere near stopping. Maybe, in the long, unhurried arithmetic of a dwarf planet's deep thermal budget, still very much in the middle of whatever timescale it operates on. There is a kind of stillness in that, if you let it settle. not the stillness of a finished thing, a thing that has completed its motion and come to rest. The stillness of a thing that moves so slowly that stillness and motion look the same from the outside, unless you know exactly what to look for and have the instruments to find it. The stillness of deep water, the stillness of a root growing through stone, the stillness of something that does not need to be fast to be persistent, that does not need to be dramatic to be real, that does not need anyone watching to continue doing what it does. The brine moves through the fractures in the dark. The vacuum above receives it and takes the water away and leaves the salt. The salt accumulates in the central pit of Cerealia Facula and glows there, bright enough that a spacecraft approaching from millions of kilometers away sees two impossible dots, and the people watching the images cannot immediately account for them. And in the salt, for however long the vacuum permits, the hydrohalite holds its water molecules in its crystal structure, patient, waiting, until it does not. And then more arrives, and then more arrives. That is the sentence the hydrohalite makes inevitable. Not as a dramatic claim, not as a declaration that anyone is certain of the precise mechanics, the precise timing, the precise rate at which the brine is still moving upward through the fractured crust of Occator, but as the only logical accounting for a substance that should, by the chemistry of its own nature, have disappeared long ago, and has not. Hydrohalite, the name is worth sitting with for a moment. In the dark, in the quiet, hydrated sodium chloride, NaCl 2H2O. Table salt, essentially, but with water molecules locked inside the crystal structure itself. The way water can sometimes be folded into a mineral at the moment it forms, held there in a tight geometric embrace rather than simply coating the outside of the grain. It is a salt that forms when very salty water, a concentrated brine, much saltier than seawater, freezes or solidifies under the right conditions, and when it does, it takes the water with it, trapping it in the lattice of the crystal. The crystal becomes a small library of the moment, holding a record of the water that made it. On Earth, hydrohalite forms in very cold, very salty environments, sea ice brine channels, polar evaporites, the crusted edges of salt flats in winter. It is not a common substance, but it is a known one, catalogued, studied, understood in its behavior and in its limits. And one of the things that is thoroughly understood about it is what the vacuum of space does to it. It dehydrates. The water molecules it has locked inside its crystal structure are not held with infinite force. Given access to a vacuum, a complete absence of atmospheric moisture, nothing to maintain the equilibrium that keeps the water in place. Those water molecules migrate outward, sublimate away, leave the crystal. The hydrohalite becomes anhydrous sodium chloride, plain salt, the water gone. And this process, under the conditions at Ceres' surface, does not take a geological age to complete. It takes, by scientific estimate, something on the order of 100 years, perhaps less, depending on local temperature and the precise conditions of exposure. 100 years. Against the backdrop of the timescales we have been moving through tonight, the 34 million years since the impact that formed Occator, the 2 million years since the youngest salt deposits formed at Cerealia Facula, the 4.5 billion years since the solar system assembled itself out of the same cloud of gas and dust, 100 years is not even a breath. It is less than a single tick of the slowest clock. It is, in geological time, the same as now. It is indistinguishable from this moment. When dawn's visible and infrared mapping spectrometer, The instrument Maria Cristina de Sanctis and her team used to read the chemistry of Ceres's surface as the spacecraft moved in its closest passes returned its data from those final low-altitude orbits, skimming just 35 kilometers above the terrain of Occator. It detected hydrohalite at Cerealia Facula. Fresh hydrohalite. Intact hydrohalite, still holding its water molecules in the crystal, not yet degraded into plain salt by the vacuum exposure that should, over any significant stretch of time, have stripped it. This was, quietly, a landmark. It was the first time hydrohalite had ever been identified anywhere other than Earth, the first off-world detection of this specific compound. And the finding was not merely a novelty of chemistry, a flag planted in the taxonomy of minerals discovered beyond our own planet. It was a clock that had already been running for however long the hydrohalite had been sitting at the surface, and that clock, read against the known dehydration timescale, said something unambiguous. The brine had not simply risen once, long ago, and dried and been sitting undisturbed since. Whatever was up there at Cerealia Facula had arrived recently, geologically recently, which is to say, within a time frame measured in centuries rather than millions of years. And it was still there, which means that it was still arriving. Because if it had stopped arriving, if the reservoir 40 kilometers below had finally sealed its fractures or cooled to the point where no further brine could move upward, then the hydrohalite already at the surface would have slowly dehydrated over those 100 years or fewer into plain sodium chloride. The clock would have run out, the crystal would have dried. And de Sanctis's spectrometer, passing over Cerealia Facula at its closest approach, would have read plain salt, not a salt with water still folded inside it, not a substance that can only exist in that form if liquid brine has been there very recently to form it. Instead, hydrohalite, still intact, still hydrated. The reservoir is not finished. The plumbing is not sealed. Something far below, in the muddy, briny, slowly cooling interior of a dwarf planet in the middle of the asteroid belt, is still moving, still, in its own patient and unhurried way, alive, and it is not only the hydrohalite that carries this testimony. Ceres has a mountain. A lone mountain, standing isolated on an otherwise relatively flat plain, with no obvious geological context around it, no mountain range, no companion ridges, nothing that would explain it in terms of the ordinary tectonics we might reach for on a more familiar world. It is called Ahuna Mons, and it rises approximately 4 kilometers from the surrounding terrain. 13,000 feet, more or less, if you want a number your body can feel. Roughly the height of Mount Rainier in Washington state, or the tallest peaks of the Pyrenees. A substantial mountain on a world only 940 kilometers wide. Ahuna Mons is not a volcanic mountain in the conventional sense. There is no lava here, no basalt, no flows of silicate rock from a heated mantle. What Ahuna Mons is, what the evidence from dawn strongly suggests it is a cryovolcanic dome. A structure built not from molten rock, but from a slow, cold upwelling of briny, icy mud. Picture a blister forming on a surface, but the blister is made of salt water mixed with ice and fine sediment, and it has been pushing upward from below over an extended period, building the dome from the inside. The flanks of Ahuna Mons are bright with streaks, deposits, almost certainly, of salt and ice, left by the material that has wept or crept outward as the dome grew. The brightness is the same signature we have been following all night. Salt, the residue of water that rose and dried. Ahuna Mons is the largest and most prominent cryovolcanic structure on Ceres, but researchers, working with Dawn's terrain data and models of how these features evolve, noted something telling about its prominence. Cryovolcanic domes on Ceres do not last. The ice that forms a significant part of their structure is subject to a process called viscous relaxation, the slow, gravity-driven flattening that happens when a solid material is not perfectly rigid. When the ice behaves, over geological timescales, somewhat like a very thick, very cold fluid, and the dome, over millions of years, settles and spreads and subsides back into the surrounding terrain. The mountain softens and sinks. The steep flanks become slopes, then gentle rises, then invisible features absorbed into the plains around them. The models suggest that Ceres should be covered in the remnants of older cryovolcanic domes that have relaxed into the surface, their forms softened beyond easy recognition over tens of millions of years. And in a sense, that is what the data shows, a surface that carries the signatures of past such events. But Ahuna Mons stands clear, its flanks still steep, its form still pronounced and identifiable, because it is young, because it has not had enough time to relax significantly, because, in the context of this world's history, Ahuna Mons is recent, a relatively fresh expression of the same internal process that continues to push brine upward through Occator's fractures. Ceres, in other words, has not only been cryovolcanically active at Occator, it has been cryovolcanically active elsewhere. The single most dramatic topographic feature on its surface is itself evidence of a cold interior still capable of driving material upward. Not a finished world, not a dead one. And then there is the water vapor. In 2014, before Dawn had even arrived at Ceres, before the spacecraft had resolved the bright spots into features that could be studied and named, the Herschel Space Observatory detected something coming from Ceres. Water vapor. Spectroscopic evidence of water molecules in the space around the dwarf planet, molecules that had sublimated from the surface or from just below it and drifted briefly into the vacuum before being driven away by the solar wind. The signal was not continuous and was not uniform. It appeared to come from specific regions, fluctuating in strength, and its detection required the kind of patient, careful spectroscopy that Herschel was designed to perform. What was detected was relatively modest in absolute terms, not a geyser, not a plume of the kind that makes Enceladus, Saturn's small moon. One of the most astonishing objects in the solar system, its jets of water ice and vapor arcing hundreds of kilometers into space in photographs that look almost too dramatic to be real. Ceres is not Enceladus in its expressiveness. It does not advertise what is happening beneath it. The water vapor Herschel detected was, in its way, a whisper rather than a shout. But a whisper is not silence. A whisper is information. And what that whisper said, 2 years before Dawn arrived, and more than 6 years before the 2020 papers laid out the full picture, was that this world was releasing water. Something below the surface was warm enough, or the ice near the surface was exposed enough to the sun's radiation to sublimate and release water vapor into the space around Ceres. It was the first sign of breath. There is also, though held with appropriate caution, the matter of what some of Dawn's imaging suggested as it orbited in its final phases. During the local daytime, when the sun's heat falls on the bright salt deposits of Cerealia Facula, heating them, however slightly, in the context of a surface that averages near -100 degrees Celsius, there appeared in some images a faint haze or brightness anomaly above the bright region. Something hovering just above the surface. something that was not there in the same way at night. The interpretation offered by some researchers was that this might be a thin transient fog or mist, sublimating ice or brine, evaporating from the fresh salt deposits and briefly filling the space just above with a tenuous vapor before the vacuum dispersed it. This observation sits in the more contested part of the scientific record. Others examining the same data were less certain that what was seen was definitively a haze rather than a photometric artifact of imaging a very bright surface in a complex lighting geometry. The science has not settled this particular question with the same confidence it has settled the hydrohalite detection or the age of the salt deposits. And so it is mentioned here, as it deserves to be mentioned, as a possibility, a suggestion, a hint carried in data that was not collected under ideal conditions, by an instrument not primarily designed for atmospheric science on a world that barely has an atmosphere. Something that may be true, and that fits the larger picture if it is true, but that has not yet been confirmed with the certainty the other evidence carries. The honest picture of what lies beneath Occator Crater is worth being precise about. It is not technically an ocean. The word ocean carries a specific image, a large body of open liquid water, the kind you can sail on or sink into, bounded by depth and distance, blue and reflective. What the evidence from Dawn and the 2020 papers describes is something different in character, though related in chemistry. A deep, briny reservoir. Yes, a layer of salty fluid approximately 40 kilometers below the surface, hundreds of kilometers in horizontal extent. But a reservoir that is almost certainly better described as a slush, a saturated mixture of brine and fine sediment and partially melted ice. A muddy, cold, dense medium through which liquid water moves and from which brine can be drawn upward under the right conditions. Not a clean ocean, not a sunlit sea, something darker, denser, more viscous, something that has been there for a very long time in the cold and the pressure of the deep interior, mixed with the materials around it into a substance that is neither fully solid nor fully liquid, but something in between. This precision matters not as a disappointment, but as an accuracy. The briny layer beneath Ceres is what it is, and what it is remarkable in its own right, without needing to be dressed up as something more conventionally dramatic. A deep, saturated brine reservoir, slowly feeding fractures in the crust above it, slowly seeping upward through an impact-created pathway that has remained partially open for 34 million years, still reaching the surface with enough regularity and enough volume to deposit fresh salt and fresh hydrohalite. This is not a diminished thing. It is, if anything, more interesting for its strangeness, its refusal to fit neatly into the categories we have ready for it. And in the context of that strangeness, it is impossible not to think, carefully and quietly, about what a briny, warmish layer in the interior of a small world might mean for the question of life. Not as a claim, as a wondering. The conditions that seem to matter for life, as we understand it from the only example we have studied in any depth, life on Earth, include liquid water, chemical gradients that can serve as energy sources, and the presence of the right raw materials, carbon, nitrogen, hydrogen, oxygen, the building blocks. Ceres checks several of these boxes in ways that would have been unexpected before dawn. The briny reservoir, if it has persisted over geological timescales, would have remained in contact with the rocky, mineral-rich material of the interior. Sodium carbonate forms in aqueous environments that involve carbon chemistry. Ammonium chloride, also detected at Occator, contains nitrogen. The deep interior would offer chemical gradients, differences in temperature, pressure, and composition, of the kind that drive the deep-sea hydrothermal vent ecosystems we have found on Earth, ecosystems that exist in complete darkness, far from sunlight, powered entirely by geochemistry. None of this is evidence of life on Ceres. None of it comes close to evidence. The 2020 papers, the Dawn science team, and the broader planetary science community have been careful and clear on this point. The finding of a brine reservoir and recent surface activity is interesting to astrobiology because it adds Ceres to the list of places where the preconditions for life are at least partially present, where a future mission might look more carefully with instruments designed to ask that question. That is a different thing from saying anything lives there. The distance between conditions of interest and habitable and inhabited is vast, and the honest position is to sit at the first of those three without reaching for the second or the third. But the wondering is real. The fact that a dwarf planet in the asteroid belt, a world long considered geologically dead, a relic, a remnant, turns out to have a briny, chemically rich interior that is still moving, still surfacing, still producing the kinds of compounds that matter to the chemistry of life. This shifts something in the calculus of where in the solar system life could conceivably have found or still find a foothold. Europa, the moon of Jupiter with its deep ocean beneath kilometers of ice, has been on that list for decades. Enceladus, with its spectacular plumes, Titan, with its liquid hydrocarbon lakes. Now, quietly, Ceres, not with the same drama, not with the same volume of evidence, but with enough evidence to deserve a place in the conversation, a dwarf planet, sitting much closer to us than Jupiter or Saturn, holding a wet interior that is not entirely cold and not entirely still. These are large thoughts to carry into sleep. They have a spaciousness to them that is different from the ordinary spaciousness of a night sky seen from a field. That spaciousness says, we are not the only place. We may not be the only moment. And whatever has been happening, slowly, in the dark beneath Occator's cracked floor, has been happening without anyone knowing about it. Without any observer, without any instrument, for all of human history and far longer, until a spacecraft no larger than a small car arrived and, in the final months of its working life, flew low enough to read what was written in the salt. Dawn fell silent on November 1st, 2018, the hydrazine, a fuel used not for propulsion but for the small thrusters that oriented the spacecraft, kept its solar panels pointed toward the sun and its antenna pointed toward Earth, was exhausted. Without it, Dawn could no longer point its radio dish back toward the planet it had come from, could no longer tell anyone what it was seeing or what its instruments were reading, could no longer accept commands or adjustments from the engineers at JPL who had spent more than a decade guiding it across the inner solar system. The last transmission was received. The last command was sent. And then, silence. But not absence. Dawn did not crash into Ceres when it ran out of hydrazine, under planetary protection rules designed to prevent contamination of a world that might, however remotely, harbour something of scientific or even biological interest. Dawn was placed in a stable orbit before its fuel was exhausted. An orbit calculated to persist not for years, but for decades. Some estimates suggest it will orbit Ceres without alteration for 20 years or more before the accumulated gravitational influences of the solar system bring it close enough to the surface to impact. And so it continues. A dead spacecraft, yes, no power reaching its instruments, no data flowing through its transmitters. No mission controllers on the other end of any signal. But orbiting still, circling the bright spots it spent its last months studying, passing over Cerealia Facula on every orbit with instruments that are no longer reading and a radio that no longer speaks. It is a strange thought, and a somehow comforting one, depending on what kind of thoughts you find comfort in at the edge of sleep. That up there, in the dark above a crater named for a Roman agricultural deity, a spacecraft from Earth is silently tracing its path around a world whose secrets it was the first to read. That the brine is still rising through the fractures below, and the hydrohalite is still forming in the salt deposits above. And the bright spots are still bright. And no one is watching them at the moment in any direct, real-time sense, and yet the record has been taken, the measurements made, the data returned to Earth and analysed by Carol Raymond and Maria Cristina de Sanctis and Jennifer Scully and Andreas Nathus and the long chain of scientists who spent years with Dawn's numbers and made the case, in those papers published in August 2020. For a world still alive in its slow and chemical way. The image that stays, if you let it, is a simple one. 40 kilometers below a cold, cratered surface, in a layer of dark, dense, minerally rich briny slush that has been there since before the impact that formed Occator, before the dinosaurs disappeared from Earth, before anything resembling human consciousness existed on this planet or any other, a liquid moves. It moves slowly, by the standards of anything we would ordinarily call movement. It seeps through fractures in the overlying ice rock. It rises, drawn by whatever combination of pressure and residual heat, and the geometry of the fractures allows it to rise. It reaches the surface, or close enough to the surface that the vacuum above finishes the work, pulls the water out of the brine, sublimes it away into space, leaves the dissolved salts behind in a crystalline crust, and among those salts, for as long as the vacuum permits before the dehydration is complete, the hydrohalite sits with its water molecules still inside it. A small, fragile, temporary record of the moment the brine arrived. A clock ticking backward. A message from 40 kilometers below that says, "We are not stopped. We are not sealed. We are still here." This is, in its way, a kind of steadiness. Not the steadiness of stone, which holds its form across millions of years by not moving. The steadiness of something that holds its process, the slow, continuous, unremarkable from the outside process of deep fluid seeking a path to the surface, across millions of years, by never entirely stopping, never entirely running out of pressure or heat or dissolved material to carry, the steadiness of a pulse, not of a wall. Ceres is 2.77 astronomical units from the Sun, on average, in an orbit that takes roughly 4.5 Earth years to complete. At its distance, the Sun is bright, but not warming in the way it warms a beach or a desert. The surface temperature near -100 degrees Celsius is held there partly by that distance, and partly by the absence of any significant atmosphere to trap even the modest heat the sun delivers. And yet, not frozen through, not inert. The interior holds enough residual heat from the original accretion of the solar system. Enough perhaps from the decay of radioactive elements in the rocky matrix of its core to maintain a layer of briny slush at depth, to keep the chemistry moving, to keep the path to Cerealia Facula, however narrow, however episodic, however slow, from fully closing. Ceres was discovered on the first day of 1801 by Giuseppe Piazzi in Palermo, and for a time people called it a planet, the missing planet, the one that should have been between Mars and Jupiter in the spacing suggested by the mathematical pattern known as the Titius-Bode law. Then other objects were found nearby: Pallas in 1802, Juno in 1807, Vesta in 1807, and the category expanded and eventually dissolved, and Ceres became the largest of a new class of objects called asteroids, and then in 2006 was reclassified again as a dwarf planet alongside Pluto and Eris and a handful of others. It has been, in the history of its naming and categorizing, many things to the scientists who tried to account for it. A missing planet, an asteroid, a dwarf planet, the largest object in the asteroid belt, a candidate ocean world, perhaps what it has always been, beneath all those shifting categories and reclassifications, is simply itself, a small, cold, water-rich world with an active interior and a quiet way of expressing that activity through salt and fractures and the slow rise of brine toward a surface that receives it and holds it for a century before the vacuum takes it back. A world that has been doing this, in one form or another, for an enormous stretch of time, and shows no particular sign of having finished. Whatever Ceres is, there is a kind of unexpected kinship in it if you are the kind of person who lies awake at night with a mind that will not stop turning. A depth that is not visible from the surface. A process running below, quiet, continuous, patient, that does not need to make itself obvious to persist. Something rising through the cracks, not in a sudden eruption, but in a slow and steady seepage, depositing what it carries, receding, returning, depositing again. A cycle that has been running longer than the human species has existed, that will likely continue running long after any visitor we send arrives to read its signs again. The brine does not know it is being watched. Or not watched. It does not need the attention. It simply moves. And somewhere in the middle of the asteroid belt, in a crater that humans named for a Roman god of agriculture on a world named for the Roman goddess of grain, the salt accumulates in the central pit of a bright feature that the Dawn spacecraft revealed to a surprised and briefly speculating public in the early months of 2015, and it glows. White. Brilliant, impossibly reflective against the dark grey of the surrounding terrain, because the water has gone and left what it carried, and the carrying continues. The spacecraft that found this is silent now. It will circle the bright spots for decades without speaking. Below it, the hydrohalite forms and slowly dehydrates and is replaced by more. Below the surface, 40 kilometers down in the cold dark, the brine reservoir moves through its own slow interior logic, feeding the fractures, sustaining the process, keeping the clock from running out. It is enough, perhaps, to rest in that. In the image of something deep and hidden and unhurried, moving without urgency through the long dark of an interior we cannot reach. Surfacing where the crust allows it, leaving its mark in salt, and then receding, and then coming back. Not finished, not stopped. Still, in its quiet and chemical way, going, the stars around Ceres are the same stars visible from here. The same light, arriving from the same ancient sources, crossing the same space. The distance between us and that crater is enormous in one sense and, in the context of the solar system, modest, a few years of travel for a patient spacecraft, a blink against the distance to any other star. We have been there, in our way. We have sent an instrument that flew low enough to read the chemistry of the salt and returned the reading before it fell silent. We know what is written there. We know it is recent. We know it is ongoing. We know that somewhere in the dark between Mars and Jupiter, something still moves. Good night from up here in orbit. I'll keep watch while you drift.